Alrighty, we're going to talk about how to write a Linux kernel module. So first I'm going to just talk about some resources, right? There's always the Linux kernel documentation, including the kernel hacking index, information about driver APIs, and even information about specific about building modules. Of course, we can read the source code or read a textbook like Linux Device Drivers, third edition, or we can read the code, right? The master documentation is always just reading it. And how to get good at writing them, obviously we have to practice. So here's an example of a kernel module, a very simple one, right? Sort of our hello world equivalent for a kernel module. We can see that we're including some Linux specific headers, right? This code will be compiled in the Linux kernel context. We have this sort of init function, which is kind of like our main function. It's a little bit different. And we also have something called the exit function, right? And we'll talk more about these things. And we have some other stuff here, right? These are actually macros. We'll talk about what these are doing, but this is indicating the license of the code, and this is telling the kernel build process which functions are our init and exit function, as opposed to there being a single name like main that is shared. But yeah, we'll dive more into this code later, but it will be our working example for this slide deck. So, as a quick refresher, we've seen this before, right? But, when we're writing kernel code, we're not in Kansas anymore. There's no main function. We don't have the C standard library, or at least not all of it. There may be pieces of it that have been re-implemented for use in the kernel, like some of the string handling functions or something like printf, right? But it's not the C standard library. It is something different, and it's part of the kernel. Goodbye to floating point numbers, right? IEEE 754, that's the standard for floating point numbers. And, hello to privileged execution, right? Running in ring 0 or EL1. Potentially asynchronously, right? And using the kernel API for things. Again, some differences, right? We have a small fixed size stacks. We don't want to be doing things like doing recursion. And we sort of have our own address space for this kernel mode, where primarily we'll be doing things like accessing the hardware. And as we know, the execution is transferred to the kernel space after a system call or some other sort of interrupt or trap, right? And of course, yeah, we have to worry about reentrant code here just by default. That in user space, right? You write a single-threaded program, you sort of opt into multi-threadedness, right? When you you have to manually opt in, right, by calling something like pthread create or whatever. But in the kernel code, you are getting asynchronous code, reentrant code by default. It is up to you to lock where needed, right, using something like mutex or whatever, where you need the code to be singly threaded to prevent race conditions or multiple pieces of code running in the same critical section. It is up to you to enforce that, right? And by default, everything is asynchronous, right? It sort of flips everything on its head relative to user-space code. Now, that sounds scary, right? So why not stick with user space? Well, for performance reasons, right, context switching back and forth between user and kernel space code is and context space within user space code, right, mean that going, if someone wanted to make something and they asked the kernel and then had to go back out and ask the user space for something, that would make the response time slower. And also on some level, right, access to hardware, right, requires privileged instructions, similar to the instructions we talked about, like the read MSR instruction, or that's the first example, right? The read MSR. There are other privileged instructions, right, that we require to be in ring 0. And so on some level, the most important drivers simply can't be handled in user space because, by definition, user space code is not running in that sort of privileged mode. Okay, so let's talk about some of the problems or some of the complexities with writing modules. In the kernel, there's something called the symbol table. It's a list of all of the global kernel items, functions, variables. All these things are exported and put into this list. But this list changes every time the kernel is recompiled. Modules can access the things that are already in the table that have been exported by other code, and they can also introduce their own exported symbols. But because this thing changes every time the kernel is recompiled, we have to recompile any modules we wish to use for the kernel anytime that we want to recompile the kernel, right? Any version that we want to link our module with, we have to compile a version of the module for that version of the code. It sort of has to be built with the same understanding of the target processor as the kernel and the same configuration, etc. when we're developing out of tree, which is what we'll be doing here when we make these modules with their own separate code that's not part of the thing, not part of the main Linux thing, main Linux repository, right? We are dealing with these problems of needing to recompile, etc. If we distribute the driver by including it in the Linux kernel, right, then we make it easier potentially, that when you compile the kernel, this thing can be compiled, right, and obviously it can be maintained collaboratively with upstream communities. But obviously, it's your machine; you can write your own code, but you have to deal with the problems of needing to recompile it, etc. Right? It's a trade-off. Um, Okay, so how do we compile modules out of tree, right? So this particular keyword, out of tree, we're talking about a work tree Git concept, right? So the Linux kernel repository has you have a working tree where you have all of the code for the Linux kernel where you can run make or whatever, right? But what if I don't want to put my code into that repository and edit the Linux kernel? What if I want to add something to it? I will compile my code in a different folder out of the working tree of the kernel, right? So that's a way that we can compile modules. Basically, you make your own folder and you develop your code within this folder. And then when you want to compile your code, you actually just call out to the kernel makefile, the same one, but you tell it where to find your code, right? And it will come into your directory and compile the things that you have set up, right? And then it'll produce files that you can load into a running kernel. So in terms of referencing this kernel makefile, right, if you built and installed your own kernel, right, the makefile for that will already be installed into the right place that will show you how to access. Depending on the kernel that's running, you'll have to use a different makefile. And for each kernel that's installed, including one that you compiled, there will be a makefile, right? But by default, if you just like download the binary image of a kernel for Fedora or whatever, one of the ones from the package manager, you're not going to have that makefile included. And so there's actually a package, kernel devel dash whatever version, right? And if we install this package, that will add it. So if you want to compile your module against a regular kernel from Fedora, right, one of the ones from the package manager, then you'll need to install this package in order to get the right makefile. But if you build your own kernel, you're also, when you install it, it will already have done that for you. Okay, so once we have this kernel makefile, right, we can make a makefile like this that references it. So basically, these kernel modules, these makefiles, they actually go in the lib modules directory with the kernel modules. So actually, I'll show that on my system /lib modules, right? I can see there are these folders, right, one for each version. These are different versions of the kernel, the one that comes from Fedora, and then actually several that have come from Fedora. I don't have one that I've compiled myself, but if you compiled one yourself, it would also be there, right? And so we can see that we're going to this lib modules thing, right? And this $shell uname-r, this uname-r command, it tells us basically the version of the kernel we're running, right? And so that will expand to this thing, and we can see that that is one of the folders inside of here, right? The 6.09-300. So if I look at the 6.09 right there, we can see that it contains all the modules, but there's also this folder named build inside of there, and we can see that it's actually a symlink to a different location, which is user source kernels, and this actually contains the source code for this kernel. So I look in there, we can see the source for my kernel, including the makefile, right? And so it's kind of a long and winding road to get to the location, right? But this -c option to make says before you do anything, right, basically change directories in some sense to the place that I'm providing here, which will change directories into this kernel source directory, and then it will try and read the makefile from there. And once it does that, right, it will execute the modules target on there, and we're providing some information. This m equals pwd, that's the present working directory, which is wherever we're running our code. So inside of this makefile, right, we put this in there with our code, and when we run this build target, it will call out to the other makefile, tell it to do a modules compilation, and tell it where to find our code by including the working directory where our code is. And then the kernel code will come in here and read this. and build our code, right? We don't build it ourselves. We just ask the kernel makefile to do it for us. There's some other targets here, right? We can ask the kernel to clean up after itself. And then I just have these targets here that allow me to actually load and unload the code. We'll talk about what that is, right? There's a command insmod to insert a module and rmmod to remove a module. We need to obviously be the root user, so we need sudo to be able to add this. And when this finishes building, we'll have a .ko file, which is our kernel object that is our module. So we'll be able to insert that into the code, and then it'll create a module, create a module within the kernel containing our code, and it will call the init function. And then if we remove it, it will call the exit function. So at the beginning, right, we had this init thing that will print hello world when the init function is called, and this exit will print goodbye cruel world when exit is called. And so as an example here, right, we'll be able to build this thing. We'd run make, and then once we've done that, loading and actually unloading the modules, here I'm just using make load and make unload. Obviously, I could type in these commands manually, right? But when I run this, it will run sudo insmod hello.ko. And then these messages that we're printing in there, they appear in the kernel ring buffer, which can be read using the dmessage command, using -t to leave off the timestamps, and looking at the last three of them, and we'll see these messages. These are from the kernel system warning us about this out of tree module, right? Generally, out of tree modules are kind of sketchy, right? And so the kernel will keep a record of the fact that an out of tree module was loaded. It was not signed in any way, and so it was an out of tree module, and it was not signed. So these are both warnings here. But then we can actually see our message there, and then when we call make unload, it will rmmod this thing, and then if we look at the message, it will cause the goodbye cruel world message to be printed. The alternative to doing this would be actually editing the kernel makefile as we did in the most recent assignment. You could add stuff directly to the kernel tree, add them to the makefile, and then compile it, right? And when you boot the system, it will call the init function. And maybe when it powers off, it might call the exit function. I'm actually not sure about that. But, for our purposes going forward, we're going to be doing a lot more stuff with modules. That's the end.